Start recording. Okie dokie. Let's minimize OBS for now. Okay, where were we? We had all this code, and we had all this commented out code, and we were drawing a triangle, and you've got that up on screen, and we could move it around. Let's try and do a little bit of cleanup before we go any further. So why don't we start by just making a new file for this and calling it transform2D. Just to keep things neat and tidy.
Must be doing something right. We're moving files now. We get to have a different file.
Yeah, I figure we've earned ourselves a file, so I'm just trying to pick up transform2D and move it off somewhere else. So we've got a bit more room to breathe, you know. Because it's starting to get to the point where, like, it's a bit messy, and we should probably sort of start thinking about clearing it down, maybe removing some of this commented out code. So why don't we just go down this file now, the original one, and I can see your code, but I can't really see what you're doing with the files because they're so tiny.
Oh,
so
sorry. Yeah,
no, that's fine.
Yeah, I just have a transform2D file separate now. So
yep, so it's all good, and I assume it's building. So why don't we just go down this file and just delete some cruft, because we have built up a fair bit of cruft. So we're load content, we're building our vertex buffer and our index buffer and our basic effect. We've got our white pixel, so that's all fine for now. We've got mouse state. What are those squigglies? You have an awful lot of squigglies.
Yeah, I mean, I use like resharper or whatever.
Oh, it's complaining because
it doesn't match its idea about what names should be. I just haven't turned it off.
Yeah.
Not a big deal.
Those things are have opinions, and those opinions are interesting.
Configurable.
Okay, so we had this target, so we were manually targeting it, and we were doing some stuff here. We don't need any of that, so it's just setting up the camera. Basically get camera. While we're in here, why don't we just optimize this a smidgen? We don't need to start with the identity. We can just start with the zoom and then multiply it. So obviously the mathematics of that should make sense because it's exactly the same result. Then we have our list of line segments. We'll leave those in for now because that's sort of like, if this was a game, that's basically the gameplay, is drawing a bunch of lines. Update, we've got...
Never mind. Keep going.
Update, we've got the scroll state. We're pretty happy with that. And this is camera motion. And we might just add some headers there just for... So that's like the first step of, like, maybe later on we'll pull these out into their own method, and just by sticking some little headings in there. If we felt they were really important, we might do that, you know. So where are we at? Yep. Okay. So then we've got the draw method. So we've got this scene, which was all of our line drawing stuff up till this point. And we have our triangle, basically, drawing. I think leave this for now, because maybe we'll want it. Let's have a look at our line methods. Were there any of those that weren't finished? So outset outline wasn't finished, so we'll just get rid of it. We can always add that back in later. So at this point, you know, if you wanted to remember that we're doing that, you know, you might want to create like add new item, where is it, text file, 2d.txt, and it's like, so you might want to just start tracking these in a 2D file. It's sort of the easiest way to do this, and that's really a matter of taste, and just check that that's not building into the build. None, do not copy content. Okay, So we have these line methods, and these are for the sprite batch way of doing things. So I'm gonna say, why don't we just leave them for now, just in case we need to reference them. But later on, I like what you're doing there. Actually, that's probably.
And they're gone.
Well,
okay, we will do it.
Yeah, why not? And this is probably. And of course this is now going to break the build, but that's very easily fixed. And that's like, I was thinking, oh, we could do that now, we do that later, and I see you doing it, and I was like, now's good. I've got a new file for it too. Why not? We'll treat ourselves to a new file.
Feeling generous with the files. It's Christmas.
What the
holidays.
heck? No, Visual Studio. Don't want that. Yes, it's Christmas. So let's just grab where'd you go? Grab these out, and
I don't think inset, outline, and no, they might be there. Yeah, I guess they're slightly different. Okay. I wasn't sure if they were done or if they were correctly named. I'm just looking. The only difference is the Z1, Z.
Well,
Z2.
you recall what those were. One's like making the lines right on the outline of the shape, and one's sort of doing like a nice, pretty inset. Okay, so that's pretty good. We've sort of reduced the amount of cruft in here. So why don't we, now we've done that, let's stick a little thing there. And we'll say these are going to be over here. We're going to do our so if at some point we decide to either get rid of one of these methods, which we'll probably do for this one, or in this case split this out into a class, we've got a rough idea of what's going to happen. So we want to add something like this back into our thing. So why don't we just copy this section of the commented out code. Actually, you know what? Why don't we copy the whole shebang? I'm just wondering how much of this we can ditch. And
then I'm gonna do this one.
Try and get rid of some stuff. So we know we don't need the sprite batch or the pixel. We'll take thickness out because we'll just use it. Why not? And okay, and then these ones, let's see, we don't really want the ones that involve matrices because we've pretty much got that licked. In fact, yeah, let's get rid of those versions. Actually, what's that? Yeah. So normally what we'd do is we'd are you caught up? Oh, you've just wiped it.
I got them in my copy paste buffer. I just wasn't sure where to stash them.
So what I've done is I've just grabbed out the the three fixed lines and the lines that we're drawing by hand. And so what we want to do here is basically do the same thing. That is, write the usage code first. And it's like, what do we want these methods to look like? And fortunately, we've already written them for the sprite batch case. And so all we need to do now is just modify them for the non-sprite batch case, in which case we can comfortably get rid of those things. It's so straightforward that I won't even sort of go through it in a great deal of detail. So hopefully what I've just done there has made a fair bit of sense.
I mean, I don't know why we're keeping it other than.
Actually, I'll tell you what we can do. I'll leave that for. Here's an interesting thing we can do. So keep that code you've got there, and I will in fact bring that code back on my end as well. What we're going to do, if true, else, and if. And so what we're going to do is we've got two versions of this code that do the same thing, and so now we can compare the different versions. So we've got one that's going to get rid of that one. I'm just getting rid of the ones that use like the use of matrices just to make things like more obvious.
Okay, I'm just gonna follow you.
Okay, so you've got that code, and finally,
I forgot the camera inverse. Okay. I deleted some stuff I needed. I get it now. And
oh, you deleted the get inverse. Yeah, I just pulled out these. I pulled out these ones up to the top just for making life easy. Okay, and now I've done that, I'm going to get rid of all of that, so that now ours should actually match.
Okay, give me 1 second here.
Yep.
The else code. I know.
Okay, don't worry about the else yet. So.
Okay.
Okay, so camera inverse, and thickness we want out of the thingy, of the if else thing. You want to grab sprite batch begin though, because we want begin and end. So this is the first version of this code. Yep, smashing. Oh, that's right. And that's what we need the inverse. So now what I want you to do is I want you to grab everything but the sprite batch begin and the sprite batch end, and just paste it on the end of this else thing. And why don't we flick it over by changing that to false, so we can get some syntax highlighting and stuff. Okay, and just we know we're not going to be drawing with sprite batch anymore, so we'll get rid of that. And that's about it. So now we know
you have a line method that's not taking. I must be missing.
No, we don't. So that's the line method we're going to write now.
Oh, okay.
So this is the vector version. So now we can just go true and build, and so now we have the old one, which is that, and we can draw some lines and we can move it around. So now we know when we switch to false, we get the new method, and obviously it doesn't build at the moment.
Mine is not very good anymore.
No, that's all right. You've just missed the endpoints. When we got rid of the matrices that were doing the transforms, you changed the start, but not the end. So now we know that this code and this code is more or less identical. Okay. And so then when we flip it over, we should get the same result.
Okay.
Cool. And because we did it before, we know that this API is basically what we want to have, I guess, is what you say. We want to do it. So just this line here. Can you see my entire screen? Like if I point to your screen, can you see?
Yeah, you're pointing at my line.
I should do that more. That's handy. Because I guess I can see my screen on your screen if I do that. Yeah, that makes more sense. Okay. So yeah, just pull out the sprite batch from that one as well. Okay, so now we have this line, and we can just use Visual Studio to say make a method stub. In fact, we'll stick the sprite batch version down the very bottom, and we'll work nice and close to where we are. So now we are in a position to actually start. Good point. Start thinking about what we're going to fill this method with. So you'll recall that what we want from over here, we have a basic effect that's going to be the same. It's got the camera matrix and the projection matrix all set up for us exactly as we want it. So all we have to do is set a vertex buffer, set an index buffer, and call draw index primitives on it. So we need to basically figure out how to get from line to a vertex buffer, an index buffer, and all the various values that we talked about last week in here. So this should be
graphics. Sorry, go ahead. I was just going to ask if the graphics device does it matter? I mean, if we're going to just call set again, we can just do that all day and it's okay.
Yep, that's
okay.
Exactly, that's fine. So basically, you set that onto the graphics device, then you set that, and you set a bunch of other stuff like this effectively sets the effect onto the graphics device, and then you issue a draw call. So the way that the graphics device basically works, where's my thingy? Whoa, slow down there, buddy. What happened there? Let me just get my thing back into an orderly state. Yeah, so the way the graphics device works is, and I can like link a thing that goes into like excruciating detail on this, but it's basically a buffer like this, and you're like, you know, do x, you know, vb equals whatever, and index buffer equals blah, and these go into like basically a command buffer, and then draw blah, and then what's happening is, you know, these things, it's like, oh, it's a draw. So then I'm trying to recall exactly how this works. It's something along the lines of this. Once you issue a draw call, it will change from like, you know, here's the useful section of this buffer to here's the useful section of this buffer, which is like that. It's like 0 to 4, non-inclusive. How do you do that again? It's like that. And then the GPU will pick that up and be like, right, well, you know, like, oh, that's changed. Let's start reading in from there and doing stuff with it. So while your program has moved on and has started issuing more stuff there for, like, you know, a next set of commands, the GPU is already, you know, ticking over these ones in parallel. So does that make sense?
Yeah, I think so. Yeah. So if you're obviously you're going to set it multiple times before calling draw. All you're doing is just wasting effort.
Exactly, and there is some, like, this is a simplified diagram because sitting in like here is the GPU driver, and it is messing with everything you're sending through. And so if you like set a vertex buffer twice, for example, it'll be like, nah, we don't need to put the second one in the command buffer to the GPU. Is basically what that's saying. And it also does a bunch of other things. It's like this vertex buffer, you know, that references off to some, you know, block of memory that's full of our vertices. So this vertex command here will contain a pointer to that, and the GPU driver will, you know, make sure that this bit of memory doesn't like get overwritten or anything before it's sent off to the GPU, and so on. something along those lines. But because this section here is basically consists of magic by NVIDIA and AMD and whatever, you can't really be exactly sure what's going on unless you spend a lot of effort, I guess, figuring that out. And so what they do on like the really big games is they're having a performance problem or something, and someone phones up NVIDIA or phones up AMD and is like, yeah, can you run this through your testing driver, your simulation thing, and tell us why this is slow, because you just don't know unless you have their access to their driver source code and stuff.
That's interesting. I mean, by the time we do it, XNA is probably deferring those sets anyway, right? We can probably set them all day and there's a lot of layers between us and them.
We'd have to look at it, and obviously FNA is different too. But yeah, there's XNA is also in here, interposed on that thing. So what ends up in going to the driver is slightly different to what goes into XNA, is slightly different to what goes in there, and so on. But okay. That's sort of the mental model you want. Is you're basically filling up a buffer full of commands, and it gets optimized for you a fair bit. So
that makes sense.
What we want to do now is whenever we want to draw a line, obviously we want to avoid we want to avoid the situation where we're issuing a whole lot of draw calls, because each one of these is fairly expensive. Like we've got this chunk of memory, for example, and that's got to get all the way from there over to the GPU. Every time we say, well, not every time we say draw, but I was thinking what's the best way to explain this, because like I said, there's a bunch of layers in between that makes it a bit confusing. But anyway, suffice to say that every time you call draw, it triggers the GPU to start doing stuff. It causes the GPU driver to actually do a whole lot of things. This, you might have heard this called the have you heard the term batch limit?
Vaguely, but not lately. Maybe not in the last couple of years.
Okay, so basically, whenever you, it used to be the case when there wasn't a GPU driver in the way, that every single thing you did, every time you set a vertex buffer, an index buffer, every time you set a doX, I don't know, matrix or set an effect or whatever, those would go basically straight onto this list and go to the GPU. And so every single one of these things had a cost associated with it that was reasonably expensive. So you wanted to avoid, this was sort of the old days, and what was it? It was called, you don't want to be changing, I forget exactly what it was called, but yeah, it's you don't want to be changing GPU drive settings regularly. Anyway, what the GPU driver does is it does some clever things, and so it, like we were saying, it bundles this all up into only the things that have changed on the draw call, and just send them all at once into the command buffer into the GPU. And what that means and what that's called, so every time you call draw, that's called a batch, which is why sprite batch is called sprite batch, is because it's sending a batch of sprites. And we want to do the same thing with our lines. We don't want to call draw for every single line, because that's going to get really slow. The batch limit is now, it depends on what you're doing and stuff, but it's tens of thousands. But even just a few years ago, it was you can send a few hundred draw calls to the GPU before you're running less than 60 frames per second. Now you can send a lot more, but it's still sort of the primary limit for what you can do if your shaders aren't complicated and so on. And this is a CPU side limit because obviously the driver is running on the CPU. So we want to basically batch our lines together. So we're going to do the same thing that sprite batch does, and we're going to make our a vertex buffer and our index buffer contain lots and lots of lines and send them all off at once, because that's basically because that's the fastest way to do it.
Okay.
So now we have some code up here that generates vertex buffer and index buffer. I'm not sure whether we stopped recording before I mentioned this, but there was dynamic vertex buffer and dynamic index buffer. And because we're going to be...
We touched on this briefly.
And because we're going to be changing the data in the buffer every frame, because, certainly these ones are fixed, and so as an optimization you could, in theory, build a static buffer and just use it once. But because we're rebuilding the buffer every frame here, and certainly in this case where the user's moving the mouse around, we have to have something dynamic going on. We're going to use a dynamic vertex buffer, which just... I wanted to explain the difference, and now I have to try and remember what the difference is because I knew it last week. The difference between those two things is, I know my diagram is getting amazing at this point. This block of memory that's filled with our vertices, if you remember, when I was scribbling this and I was drawing this line, I was like, it's got to get all the way to the GPU. What happens if you have a dynamic vertex buffer and you start writing into the vertex buffer before this copy is finished, if it's just a regular vertex buffer, you will stall the entire system until the copy is finished, and so you lose the parallelism of the GPU. If you have a dynamic vertex buffer, it will do, I think, some sort of copy on write system where it's like, okay, you want to write into this vertex buffer, we're still using it, so we're going to make a copy of it for you, and you can start writing into that instead. And so the next time a draw comes around, it's like, please use that vertex buffer, and it will use the copy. And so because I think it's copy on write, which means the copy is a bit faster than what would happen if you stalled the GPU, because the GPU could be like several frames behind or something, so it's like it's not going to get to copying that vertex buffer in for quite some time, whereas you want to modify it now and keep issue more calls up here. So you want to keep the CPU moving, so you want to just copy that and start writing to it straight away, rather than having to wait for the GPU to finish what it's doing. So that's why you have a dynamic vertex buffer or a dynamic index buffer. It's it's a little bit different for textures and render targets, kind of. And just, yeah, I think, I don't know the exact details off the top of my head for how it works for textures, but it's kind of similar. So does that make sense?
Yeah, I mean, there's a lot of structures in distributed computing that use copy on write semantics for like multi-threading and trying not to get, trying to for performance and
exactly
locking and IO and stuff. So the concept is familiar. So it makes a lot of sense. It's just like, strikes me how many layers are trying to do things the right way so that we can just, set stuff and then draw it. But it all makes sense to me. Yeah, it's pretty cool the way it works.
I can send you an article that's like, I think it's like 11 very long blog posts or something by someone who really understands this stuff, or understood it, because it keeps changing. But it is excruciating in its detail. Okay, so we have a dynamic vertex buffer, and what we want to do is we want to, what are we going to call this? This would be like our line vertices. And as we saw over here, we're up in load content. We have to like fill this with stuff and instance it and stuff. We want to do a similar thing down there, but to make life easier, we're just going to make another method just so we can keep the code next to each other. Vertices equals new dynamic vertex buffer, graphics device, and now we need to decide how many lines we want to draw. Because as you will have noticed sort of before, the size of our buffer is fixed, and we have to decide that buffer ahead of time. So we know that we wanted, for the time being, the same as we had before. So that was vertex position color. So let's have a few of those. Okay, and so this buffer usage write only is sort of similar to this situation between dynamic vertex buffer and a regular one. It's just making sure that the I guess reading semantics don't lock the GPU. So if we're saying we're never going to actually read from this buffer, we're only going to write into it, it doesn't have to do a whole lot of management of that side of things. So we need some number of vertices, and we have maximum lines 1024. Now we know that when we draw a line, that it's basically going to be a shape that looks like this, with two triangles between 4 vertices. So we have 4 vertices per line, so that's what we need to put in. So 4 times max lines. Now, we don't want a dynamic index buffer, at least for this particular exercise, because we know just ahead of time that we're never going to change the way that indices are allocated. So if this is like line number 1 and that's line number 2, this will be 0, 1, 2, 3. We know it's going to be like, in fact, it might make more sense to make it 0, 1, 2, 3. And this next one would then be 4, 5, 6, 7. Then we know that our index buffer is going to be like 0, 1, 2, going clockwise, and then 1, 3, 2, and then we move on to this one. It's going to be 4, 3, 6. Just draw the right number. 4. Oh, sorry, I can't read my own writing. 4, 5, 6, and then 5, 7, 6. 6, and so on. And this is never going to change because it doesn't matter where we draw the lines. They can be out to anywhere. And also, we know that when we were drawing the lines, when we were drawing the triangle before, where did it go? Draw index primitives, we actually get to specify how far into the vertex buffer, and the primitive count and primitive type tells us how far into the index buffer we read. So yes, I see you jumping ahead there, which is good. New index buffer, graphics device. Now you do have an error there, so
whoops.
That's okay. 16 bits is fine. Actually, we should calculate that because it's going to depend on how many vertices we have. So if we have let's bring up calculator. We have 1024 vertices. 1024 lines times 4 vertices. that's going to fit into 16 bits, so that's fine. If we had like that many lines as their maximum times 4, that still fits in 16 bits if it's unsigned, and I think it's unsigned. But so you can imagine if we had that many lines, suddenly we have more vertices than we can fit in 16 bits. But that's not the problem. Bring back the thing here. So you'll notice that for every line, we have 6 indices. Because we have 2 triangles per line.
2 triangles per line. I was only doing half the triangle. Yep. Half the line. Okay. Yeah, that's so I get it.
That's not a problem. So, and because we know this is fixed, whoops, we can just go ahead and fill it now. So why don't we do that? For I equals that to max lines. Now we need a buffer to fill it with. So So hopefully you can see what I'm doing here. I'm going to need to cast it. So so each of our 6 indices refers to one of 4 vertices, and so we'll remember what they were before, just out of memory, as 1, 2, and then the other one was 1, 3, 2.
Now, aren't we allocating a bunch of memory we would not use until we had all 1024 lines on the screen?
So yes and no. So this is the simple version now, which just has a fixed number of max lines. And what we're going to do here is we're just going to be like, I'll jump ahead a bit and be like, less than max lines. And then if we get up to max lines, for the time being, we're just going to go and not draw anything. Else nope. And I mean, yeah, you can write that in. In fact, why don't we write that in there? Yeah. If we're feeling generous to like our future selves, we might write so we could do a thing, and I'm thinking for the sake of this particular exercise, like this is just doing the same thing over again, but handling the case where you run out of lines. So in that case, either you reallocate this whole thing so it's bigger, or you start allocating, like that might become a list of and you can reuse this set of indices, but this might become a list of vertices. And from memory, I think this is how XNA does it, because we've already told this thing that we're not going to read from this, so we can't do the expandable version because we can't read out and copy to a different buffer because we're write only. So we have to start making new buffers and drawing, I guess, multiple buffers. If that makes sense to you, does that make sense?
Yeah, that does. It's similar to the copy on write thing, and we're going to just make a bunch of write only ones and link them together. But I think that,
yeah.
What about the opposite case? I mean, I was thinking, that's a good point, but I was actually thinking about the index, the line indices themselves. I mean, we're allocating this. I guess it doesn't matter, right? We're allocating like 6 in 16s times 1024, and we're allocating, like, we're pre-allocating that in fixed memory. It's going to be like nothing. Then I'm worrying about the wrong thing, right? You're about to tell me it's 12K? Okay.
It's 12 kilobytes. And
right.
In the grand scheme of things, like, that's not that much, really. Like, you could probably make that bigger, but 1024 is like roughly a good number. It's not too much. It's not too little, so you're not having to constantly reallocate this one anyway. So it's not a big deal. And the nice thing is, obviously, yeah, this gets shared between every single set of line vertices we do. What I will quickly just run over, we have another little aside over here because it's kind of I'm gonna figure out why I keep zooming out. It's sort of basic computer science theory, so you might know this, but do you know what happens when you go, list t dot add if you do that a bunch of times, do you know what the memory does behind the list t? Like, do you know how it reallocates the buffer in there?
For my recollection is that basically it sets a default capacity. I think it's 10 or something, and then once it gets to the point where it's halfway done, it's gonna double the buffer underneath and rewrite it all.
That's pretty much right. It doesn't actually wait till it gets half. It waits until it's at capacity completely. So
okay.
if that's like 10,
that's gonna cause a frame drop on it, and you like have to stop what you're doing and grab more memory.
Well, this is getting into .NET's thing as well, because it's a bit different if you're in native code and you're running. If you're not garbage collected, you would have to delete this. Well, not delete, but free this memory up after you've and add it back to the free list after you've found space for the doubling. So this is now going to be like another 10 for a total of 20. So it doubles in that case. Actually, yeah, this sort of is getting to what I was going to say. In the garbage collected case, allocating another 10 is like a trivial operation. It's exceedingly fast, but then it's going to go have to and find, because the old buffer of 10 will get no one's referencing it anymore. So when the garbage collection comes around, it has to deal with that excess memory, and obviously allocating the 20 for the next buffer is going to possibly trigger a garbage collection. So it's a little bit different in this case, but the reason that it doubles is sort of what I was gonna get to. And are you aware of the reason that it doubles?
I am not.
So this is a fun bit of comp sci stuff, and I'm just trying to think of how the best way to explain it is, because I can just tell you the reason, and that is amortized cost. And so what that says is every time we add something to the list, we're taking it from there to there. That's one memory copy, basically. And we'd like all of our adds to be one memory copy in cost. However, once we run out of buffer, once we get over here and we need to copy that sucker in, we've got this one memory cost, but we also have to expand our buffer from, it was 40 just then, and now it's 80 now. So that's 40. I guess that's really not a sensible thing to draw there, because in no instance do we actually allocate that as 40. But this whole buffer is, up to this point is 80, and that's 40, that's 20, 10. And so what happens is we've got a copy from this buffer, which has got 40 items in it, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 over into, well, I've drawn them over the top of each other, so, 1, 2, 2. And what you find is that, and this is the bit where I'm going to have to skate over the maths, because I actually hadn't gone and read this and got the exact maths right, but you'll have to trust me on this one, is that the number of copy operations for a single element gets amortized across when you double it, so that the cost of doing an add operation is big O1, or rather more properly, it is big O k, where k is a constant factor. So like this add is going to cost a whole lot, but these ones are relatively cheap, is basically what happens. And when you double every time, you basically cause the cost of this massive copy here to be spread across adding. So you have to copy that many elements to move to a new thing, but you've also added that many elements in the past. So effectively it's 1 plus 1 that will happen in the future when you add. Does that make sense?
Yeah, it does. Other than not understanding the rudiments about why the memory needs to be contiguous, why copy at all? I mean, we already have 1 to 39 or whatever in memory. Why aren't we just like keeping a little map like where it is, instead of throwing the whole thing away and looking for 80 bits?
Okay, so there's, I guess, 2 reasons why you'd want that. The first reason is contiguous memory is fast. If memory is back to back, it's just fast. Now you can why don't we make a new layer and just draw out that particular situation. Contiguous memory is fast, but you could ignore that if you said, here's one block of that list, and here's another block of that list, and we happen to know, because we've done the allocation in a clever way, that like that block happens to sit on a memory page, or well, a memory page is not a memory page. It's, it will be a memory page as well, but a cache line. So that when you pull in read that, it will pull in this whole thing. So when you read all these, you get exactly the same performance, more or less, as if you had one in here as well, and it was contiguous. The only downside is that modern CPUs, if you read that element, and more or less if you've read that element and that element, it will go and say, oh, you probably want this element next, and it will actually prefetch that cache line. So in fact, having them properly contiguous is actually a small benefit over having them in the same cache line, which requires them to be contiguous on a cache line. But the data structure you're talking about would be let me back out that change, so we have 2 separate things. That's all right, well, here's my first block, and then here's my second block, and then Here's my third block. And so the thing, what you've done there is you've just moved the problem one level up. And that is, this now has to be contiguous. Sort of. This has to be contiguous, and you've added in this pointer chasing. So now when you want to read, say, this element, you have to actually first read into this table here, and then find that element, and then read into this table here. So you've actually now, instead of fetching one cache line, you've fetched 2 cache lines onto the
I was thinking in terms of maybe it being good enough for most cases, but yeah, it makes sense.
Mm-hmm.
I don't want to derail it further, but I think this cache line stuff, you were leveraging that in RCRU for when you were. I just remember a time you were talking about cache coherency and even accessing variables in a particular order or a particular way.
Yeah.
For performance reasons, it's an interesting topic.
Yes. So yeah, what I would say about that is, like, if you're really hardcore, you can like calculate this stuff and measure it and stuff. But the simplest thing to do is just think about, how is this laid out in memory? How many, like, if am I chasing a pointer through there? You know, am I going to have to grab in 2 cache lines, or am I making a data structure that's like that big? And so, you know, if I'm getting stuff here and here, I'm going to bring in, you know, a second cache line. If I can make it just that much smaller, I can always be like grabbing off this one cache line, so it will fetch less. And if it's contiguous, you know, maybe the data structure is that big. Maybe I can get like 2 data structures at once, particularly if I'm like processing them all in order. And as I was saying before, if they happen to do that, and the CPU, if we're running through it that way, if the CPU is prefetching, it will grab this cache line for me before I need it. So it just makes everything a smidgen faster. But that's about as much detail as you really need to sort of leverage that. It's like, let's make everything contiguous, and if we can make it small enough to fit in a cache line, particularly if it's high access, that's extra bonus. But what I was going to say is, for the purpose of the line drawing, we may actually want to do this arrangement here. In fact, this is exactly the arrangement we have. This is the list dynamic vertex buffer, and this is, you know, a bunch of dynamic vertex buffers, because, as we were saying before, we can't do the thing where we expand the actual dynamic vertex buffer, so we're forced to do it this way. However, the you know, the O1 thing, this access here is a constant cost as well, so we can still be constant cost to add a vertex if we make, you know, this one is going to have like, and this one is going to have like 2, 4, 8, you know, and so on. So we could do that. The only downside to doing it that way is obviously we're limited to how many indices we have in our index buffer. So we might want to do this, but then maybe we just keep it simple and do that. It's like, how many times are you going to draw 4,000 lines on a screen at once? Probably not very often.
Geometry wars?
Well, in those cases, you might in fact expand this number here out to be huge as well. Just be like, yeah, we know this is going to be big, so we're going to start big. Anyway, so that was a nice little digression. So we have our index buffers, we have our vertex buffer. It's ready to write stuff into. What else do we have up in our load content? I think that was it. We had vertex buffers, and we had index buffers, and we had the effect, which we're going to reuse the same effect, so it'll be exactly the same. So now all we have to do is add lines to our vertex buffer. So, and this is where this outline thing we had before comes in handy, because we're actually figuring out the 4 vertices. So you'll recall, like, way back when we did outline, it's like, this is why we're doing outline, because we want basically certainly this maths here. So let's copy outline and hope that we have that correct. Huh? How confident are you in that code?
I don't quite remember it, so perfect. Wait a minute. My outline code is different than yours.
I have a variable called p. What's x on yours?
No
Oh,
idea.
I folded x into p, so I've folded that divide by 2.
Oh, I see. Oh, okay. I didn't even. Ow.
So rather than modifying outline, because we know outline works.
Yep.
So I just copied it up here, because we no longer have border thickness. That's the point. So that was height in the old code. And this is why naming things is obviously important, because you need to know roughly what everything means. I guess height is not too bad, but we'll call it thickness now.
I'm confused though. Why are we tapping back into the line batch stuff?
So, well, we don't want this. What we want is the points A, B, C, and D. So in fact, we don't really need this at all.
Right.
And we want to add these to our vertices. I'm just trying to think the best way to do this. So you'll see how we set the index buffer like this, and earlier we set the vertex buffer with an array of vertex position color. Let's just keep that array in memory and work in that, because we're going to have to do a lot of set data. Like if we're calling set data in here if we're doing that every time we go to draw a line, basically you remember this diagram here, we're filling up this thing potentially. Certainly we're putting a whole lot of nonsense into the GPU driver. We'd rather touch the GPU driver as infrequently as possible. Typically ends up being the most performant way to do things. So we'll build up the entire buffer all at once, and then once we're ready to set it, we'll set what we need. Equals new, and we know exactly the size of this already. And so this code is going to look an awful lot like this code here. So it's going to be like, well, where are we up to? We're adding the line count vertex, and there are 4 vertices per line plus 0 equals new 3, and then finally increment the line count. And all we have to do now is, does this have a constructor? Maybe not. Okay.
I think it does. Yeah, it takes a vector 3 and a color.
That's weird.
Could be an FNA thing.
I think, well, for starters, we've got vector 2s. So we're going to have to convert them, obviously. I was wondering, it wasn't auto-completing for me, which is very unusual. B. So we've got A, B, C, and D. We want to make sure that these match up with what our indices were. So we just go to the diagram for this. So if this is A, if we call if we call this side the start and we call this side the end, so 1 and 3 are on end and 0 and 2 are on start. So 0 is A and 2 is, well, let's make it on start.
C. Oh, it's what?
I'm just going to reorder A, B, C, and D.
Okay.
So that they match our diagram. So we had A is going to be 0. In fact, I'm already using V. I'm going to rename these. And the reason that I'm going to rename them is because they match what we're sticking into our index buffer. So 0, 1, 2, 3, whereas ABCD is a little bit confusing.
I see. Yeah, this is redundant because this constructor is better.
So, that seems pretty good to me. What do you think?
I was a little harder to follow that.
Well, before we move on, I mean, where are you at with this code? How are you feeling about it?
No, I'm good. I just it just seems a little bit like magic to me because like all we're doing in the outline is getting the maths for the maths is the same, start position and end position, and no, I don't know. It's fine. It's fine. I mean I know what's happening. It's fine. I mean, yeah, I'm good now. Just you had a late lag time in my brain.
Yeah, no, that's fine. I was quite happy to give you a few minutes to process that one, so it's making sense. And we'll now, so it's very similar to what Sprite Batch is doing anyway. It will build up a dynamic vertex buffer, and it's just its code here is for sprites rather than lines. So if we scroll back up to here, you'll notice the Sprite Batch version, it's got SB begin and it's got SB end. And what happens in SB end is the same as this. All of this stuff here, it sets the vertex buffer, sets the index buffer, sets the effect, and all the other stuff that's necessary to draw the Sprite Batch, and it spits those out to the GPU. And that all happens in end. Now, so we basically need our own equivalent of end. So let's just call it finish vector lines. And that's going to be pretty... Yes?
We haven't really called set yet, though. I mean, I guess we're doing that because we're retaining it, right? We're just... And then we haven't done the work yet. I mean, we
exactly.
Haven't in memory. Oh, okay. That's what you mean by end.
Yep. Oh. And so, yeah, so what I was saying before was, like, this set data call could be expensive, and I haven't measured it, and I can't remember what the current GPUs do or any of that stuff, but it's possible that that's expensive, and it's really fast to do this, and we're going to have to call set at least once anyway, so better we just call it once with a whole block of data than to do it with a whole lot of tiny little bits of data. And that's just generally good advice. Like, if you find a thing that's like, you can do this 1,000 times with tiny little blocks, or you can do it once with one massive block, it's usually better to work with just one massive block for pretty much everything.
Yeah, that's for sure. Yeah.
So let's do that now. So we've got our line vertices, set data, line vertices data. Now, this has got some overloads, and we might want to use some of these. Because we know that we've not necessarily set every single one of these vertices, so why bother copying vertices we don't need? We might also do this if because obviously we can do that very quickly, and sometimes APIs like the GPU stuff will be like, what, you tried to draw nothing? Can't let that happen, and like chuck an error. I don't think I don't think it does in this case. I think you can actually draw nothing. But let's just not even bother going there. So we've set the data. Now all we need to do is we come up here and we'll just grab our effect drawing code. And we'll come back down here and just paste that in. So this is all very simple, just an expansion on what we were doing before. So the last thing we need to do is, obviously we need to make sure these are the right buffers. And we need to figure out where our start positions are. How many we know the number of vertices because we just set it over here. Start index 0, and we know the primitive count because it's 2 times the number of lines that we're drawing. And in theory, if no one's made any mistakes, which is always possible, that should be everything we need to do to draw lines, except one last thing, almost forgot, line count equals 0 after we're done.
Wait, I thought the line count was what we were retaining in the game itself. I must be wrong. It must be the line segment. That's the state. The line count.
Yes. So this is part of the downside of doing this all in like the single game class, and that is sometimes you get like confusion of, you know, what's where. So if that starts to happen, maybe you could be like, well, let's make a static class or something to put this in. But
it's just interesting to me that we have to track with state the amount of lines that we've drawn to make sure we don't go over the number of lines that we've set. Anyway, I guess that's fine. I guess I don't know why we're sending, like, we're gonna, in this case, like with only a couple of lines or even none, like we're basically setting data with like 12,000 zeros or whatever, and that's, the GPU is okay with that.
Well, what we're doing, we've got the buffers ready in case we need, because we want to avoid doing that expansion thing, because as we talked about, that's going to be expensive.
That's right.
But over here, when we call set data, we're actually only sending that many elements there. So it's actually, for very few lines, it's actually going to be nice and snappy. Like, I mean, obviously it's going to be really snappy anyway because it's not doing much, sort of heavy CPU wise. But anyway.
I misread it. I misread the code.
Yeah, no, that's fine.
We have a lot of variables with the word line in it. All right, I got it now.
Yep, good. Let's
press,
give this a red hot go.
Where are my rectangles?
So, on the plus side,
nothing.
Mine works, which just means that there's a difference between your code and my code that was probably really easy to fix. So why don't we go and look into that? Because this is always the fun bit. There's a bit of debugging.
Yours seemed to do something pretty cool there. It looked like when you were drawing it, the line was a different color, and then when you let go of it, it like faded out.
Oh, that's just this code here. In fact, why don't we start up in our draw method? Just make sure our draw method's the same. It should be. Yours does. Oh yeah, yours does the same thing. No, it doesn't. Yeah, I just removed the times 0.8 there for the drawing one.
I see.
So it just fades out.
Yeah. The active one is more. Is opaque, and the final one is less. So.
Exactly. So,
okay.
That all looks the same to me. And are you calling finished vector lines? Yep. And the triangle's drawing, so that's always good. So let's have a look at what our vector-based lines are doing. So it looks to me, given your squiggly, that maybe line vertices data is not getting set properly.
No, this is just my resharper jump.
Resharper is complaining. That's all right. Well, that's fine.
I'm going to turn resharper off because it's only really good for city business development.
Yeah. when you're making games and you sort of understand what you're doing, you kind of want to turn off some of the little helpers. So you're making your buffers okay. You're not getting any errors from these buffers, so that seems
I'm
good.
building. I mean, it's not drawing it.
Now,
I bet you. I mean, it's got to be something in there.
Can I have a look at your load line content just to be sure?
Yeah.
Yep. Okay, found the bug.
Oh, I should probably set it and stuff.
Yes.
Yeah.
I think, because obviously that's all going to be zeros, which is going to be not very many triangles, or they're all going to be degenerate triangles get drawn.
Indices. We have I guess we spelled them differently. All right. Good.
Have I misspelled the word? Probably. Ah, smashing. Oh, easy peasy.
It's beautiful.
And you'll notice there's, nice and crisp vector lines. Now, how are we on time? We're probably.
No, we're way off. Way past.
Oh, not that far past. A little bit. So it's probably a good time to finish up. So what we might do next week is we'll have a little digression into pixel shaders, so that we can do those fancy end caps. So we'll add some triangles on the ends. It should really be very simple, but it means that this will just be the same thing but adding some more triangles. So just modifying the code slightly, and then we can look at just how to do a real quick pixel shader and some of the stuff that goes into pixel shaders, because we haven't done pixel shaders yet. So we might spend a lesson on that.
No, I don't think I have any experience at all with shaders other than what we cobbled together of mine and together.
Well,
pretty fundamental for me.
I'll try and come up with some interesting stuff to talk about for that. So let's go and grab OBS and take us offline.